Okay, we're up to video 21 here and starting chapter 7, which is all about quadratic forms and symmetric matrices and how they're all related. So we'll start with a definition here. A symmetric matrix A is such that A transpose equals A. So for example, 1, 0, 0, the identity matrix is symmetric. The 1, 1, 2, 3, nope. Not symmetric. How about A, B, C, B, D, E, C, E, F? Yep, that one's symmetric. Basically, if you draw a line through the diagonal, all the other ones need to be the same. And that gives you the symmetry across the diagonal. Okay. And there's a series of really powerful theorems in this section that we use over and over again. So if A is symmetric, then any two vectors from distinct eigenspaces are orthogonal. Okay. And I'm going to go through this example a little more in depth than the book does because I think it's important to see how this plays out. If you're given the matrix A, which is 6 minus 2 minus 1 minus 2 6 minus 1 minus 1 minus 1 5. So 6 minus 2 minus 1 minus 2 6. Okay, so the eigenvalues of A are 3, 6, and 8. All right? And the eigenvectors corresponding to these three, so which is the first one will be the eigenvector corresponding to lambda equals 3. You get 1, 1, 1. Let V2 be the eigenvector corresponding to lambda equals 6. And it's minus 1, minus 1, 2. And then V3, which is the final one, is minus 1, 1, 0. And this corresponds to lambda equaling 8. Okay. Now, if you compute all of these dot products, V1 and V2 is 0. V1 dotted with V3 is 0. And V2 dotted with V3 is also 0. So this set is an orthogonal basis for R3. Right? We showed they're orthogonal. There's 3 of them, so they cover all of they span R3. Okay, so we now have an orthogonal basis. Let's make it orthonormal. So the length of V1 is what, square root 3? So the first vector becomes 1 over root 3, 1 over root 3, 1 over root 3. Let's see, the length of vector 2 is root 6, so you have minus 1 over root 6, minus 1 over root 6, 2 over root 6. And the last vector has length root 2, so you get minus 1 over root 2. 1 over root 2 is 0. Okay. So I'm relabeling these as V1, V2, and V3. We just scaled them by whatever the length is. Okay, so now we let P be these 3 column vectors. Okay, and we're going to let D be a diagonal matrix, and these have to go in order with diagonals 3, 6, and 8. And from work, since P is orthogonal, we know that A is equal to P D P inverse. And since P is orthonormal and orthogonal, this is P D P transpose. Awesome. And so this leads us to another definition. A square matrix A is, here comes a long one, orthogonally diagonalizable if there exists a P which is orthogonal and invertible such that A equals P D P transpose, which is P D P inverse. So now we have a stronger form of diagonalization. We have orthogonal diagonalization. And this leads straight away, we just worked out through examples this theorem. A is orthogonally diagonalizable if and only if A is symmetric. And one leads to the other. Okay. Now when I got to upper division math courses, we stopped calling eigenvalues and we called them, so eigenvalues of A are called the spectrum of A. And your book doesn't use this notation, but my notes from college do, and it's written spec A. I probably won't use that because the book doesn't, or maybe it'll show up somewhere, but it just means the eigenvalues of A. And spectrum, well, there's a reason for it, but I'm not really clear on what that is. Okay. This is a really famous theorem. It has a name. It's called the spectral theorem. I vaguely remember proving this for some class in grad school because the proof is not trivial at all. And so you start off with, so you let A be symmetric. And there's 4 things here. 1, then A has n real eigenvalues, including multiplicities. And your book writes this differently. I don't like their notation, so I think mine's much better. For each lambda in the spectrum of A, the algebraic multiplicity equals the geometric multiplicity. C, all the eigenspaces are mutually orthogonal. And lastly, this is the theorem from before, A is orthogonally diagonalizable. All right, so part D of this is just theorem 7.2. So the spectral theorem collects all the facts and stuff and theorems from before. Okay, now what the spectral theorem does, it gives us a way to decompose a matrix A. And so this is a really interesting construction. It really lends itself to what's going to happen next with the quadratic form stuff and how to get those functions. So remember, so this is going to be some form of construction here. Remember that A is PD P inverse or PD P transpose. All right, so this is just there to help us. Now we know that the columns of P are equal to the eigenvectors of A, and they are orthonormal. Okay. So in particular, we're going to write P as U1 down to UN, where U1 to UN is the basis for Rn, and they're all eigenvectors corresponding to distinct real eigenvalues in A. And D is going to be a diagonal matrix loaded with the eigenvalues. Okay, so we know that A is equal to PD P transpose. So because it's in column form, it's nice. We have U1, UN, and then so that's P, and then D is going to look like this. It's going to be lambda 1 down to lambda n with zeros everywhere else. I went a little further down there than I wanted to go. Oops. And then P transpose looks like this. So each one of the column vectors in P is now over here is a little transpose. Okay. All right, when you do the first matrix multiplication, you get lambda 1, the vector U1 plus dot dot dot, lambda n vector UN. And now we have this guy sitting over here. Right? Okay, and now you put that whole thing together and you get that A equals lambda 1, U1, U1 transpose plus lambda n, UN, UN transpose. And this is called the spectral decomposition of A. Now, the key here, well, this is a key fact. Each matrix UJ transpose is a projection matrix. Since for X in Rn, we have UJ uj transpose of x, this is equal to the projection of x onto the subspace W, where W is the span of the UJs. And so the spectral decomposition projects vectors in Rn onto the span of the orthonormal basis vectors. And I should have here u sub j equaling 1 down to n. Okay. All right, and we're going to use this in the sequel to do some fun stuff. So here's a little bit of housekeeping. We know homework 8, well, it was due today, right? Yeah. That's in. Homework 9 is going to be due on November 9th, and it's going to cover sections 7.1 through 7.3. Homework 10 is going to be due on the 23rd. And then homework 11, I'm not sure when that's going to be due, but it's going to be our final exam cheat sheet plus a surprise. Okay. And there might be a couple more, 2 or 3 more workshops. So approximately 2 or 3 more workshops just to get some more grades in the book. When all the workshops will come in as problem sets, and then the final will be on the 10th. I think I cut it down to 20 minutes. Just so we can be done in 4 hours instead of 6. Because like I said before, I wanted to break it up into a couple of days, but you guys weren't having it, so it's understandable. So yeah, and I'm gonna stick to these dates. I'm not sure what problems are going to be for everything yet, because I like to do that as I go along. I do know that for section 7.1, you're going to have problems 16, 19, 34, and 35. I haven't decided on 7.2 yet, and I'm just getting to work on 7.3 to make the video. So, all right, this stuff is really interesting, especially when we get to the next set of videos. 7.2 is a two different parts of videos, because it's really dense, and there's a lot of geometry that's floating around that I really like to play with. So I take my time with that one, and then we move on from there.